Welcome to this lecture series in group theory. Let us recall a few things. So let G and H be groups. Then we call a map from G to H a group homomorphism if the structure preservation condition is satisfied. We define the kernel of a group homomorphism as the set of all those elements of G which map to the identity of H. The image of phi is, well, exactly the image of phi. It's a set-theoretic concept, not a group theoretic concept. And we saw that kernel and image are subgroups of the respective groups. So kernel phi is a subset of G, but it is a subgroup of G, and image phi is a subset of H, but it is actually a subgroup of H. And we saw another property that phi is injective if and only if kernel phi is the identity, the trivial, the smallest possible it can be. All right. These are the problems. And let me say a few words about this problem. I am not going to use this problem here, even though I've marked it as star. This is not a hard problem. Star marked does not mean hard problem. So let me not mark it as star. Let me just mark it as something else, maybe a tagger. Okay, so let n be some positive integer. So there are two different groups or different looking groups that one can consider. One is the set of all the linear isomorphisms from Rn to Rn. And that's a group under composition of linear maps. The other is the set of all the invertible n cross n matrices with real entries. And they, of course, look different. The description is very different. This guy is containing linear maps while this is containing matrices. But there's a simple way to go from linear maps to matrices once you have a basis. So using that, one can easily show that there is an isomorphism between them. And this is why a lot of times, depending on what is convenient, one uses this notation to either mean the set of all the linear isomorphisms or the set of all the invertible matrices. And I will also fudge these distinctions as we go forward because everybody does that and it's a good thing to do. All right. So let me also mention one thing which I should have mentioned in the last lecture is a property about compositions. So suppose we have two group homomorphisms which are composable, meaning the target of one is the domain of another. Then the composite is also a group homomorphism. And this is a very straightforward exercise. So I leave that, but I should have mentioned this in the properties of group homomorphisms. Okay. So now we go to the material of this lecture. First, we need a little bit of a notational definition. So fix a group and fix two subsets of the group. Define this notation a dot b or just simply ab as all the elements that you can form in this fashion where little a is chosen from capital A and little b is chosen from capital B. So this is just a subset of the group. A and B are merely subsets. They are not meant to be subgroups or anything, just any two non-empty subsets and you can form this. All right, so here is what we want to prove. Suppose we have a group homomorphism and G1 and G2 are two elements of the domain group. Then this thing, which just think of this as capital A and think of this as capital B, then we want to show that this thing is actually equal to that. So let me remark that potentially the size of this, or the size of this guy, could be size of A times size of B, provided they are finite, of course. We are not assuming they are finite, but if they are finite, the size would look like, typically we would expect at least that the size would be of this sort. But in this special case where you have A and B as cosets of kernel, the size is not getting multiplied. The size of this is same as the size of that. So it's interesting. Anyway, so let's prove this. What we need to do is the following. So let K1 and K2 be arbitrarily chosen in the kernel. And we will show that, or rather we need to show that to show this containment. First we will show this containment. To show this containment, we need to show that G1 K1 times G2 K2 is in that. So this is what we would like to do. Right, so how do we do it? We have G1 K1 G2 K2 equals, this is a little bit of a trick, G2 G2 inverse K1 G2 K2, and let me bracket it in this fashion. And the key fact is that this is also in the kernel. So this is some K3, and how do you check this is in the kernel? Just apply phi. So it is phi G2 inverse K1 G2 is phi G2 inverse phi K2 phi G2 But this is identity, so this kind of goes away. So we are left with phi g2 inverse times phi g2. But this is identity because phi g2 inverse is inverse of phi g2. So I leave you to fill the details. Basically, just verify that this is in the kernel. Therefore, this is equal to g1, g2, k3, k2 for some k3 in the kernel, and which is an element of g1, g2 kernel phi. So what we have shown so far is this containment. Why? Because we picked some arbitrary elements in the kernel and considered this. So basically, it is as good as picking an arbitrary element from this and an arbitrary element from that. And we took the product and showed that it actually lies there. Therefore, this containment holds. Reverse containment is immediate because I will not write the details, but for the reverse containment, just note that g1, g2, k, where k is chosen arbitrarily in the kernel. So this is an arbitrary element of that guy, but this is nothing but g1e is the identity of g, g2k, which is of course of this form, because g1e is here because identity always lies in the kernel, and g2k is here because k is in the kernel. It was chosen that way. So this will show reverse containment, and hence we have that. So this was just a simple exercise. I could have given this as an exercise, but anyway, I gave all the details. We will use this in this lecture. Okay, so now let us recall a simple set theoretic fact, which if you have seen my linear algebra lectures, I have discussed it there. But let me briefly recall what it is. So we have two sets, x and y, no structure, no group, anything, just two sets, non-empty sets, x and y, and we have a map from x to y. So then there is an equivalence relation that f induces on x. What is that equivalence relation? So we define x1 tilde x2. So tilde is a relation on x, which is defined in this fashion. All right, check that this is an equivalence relation. That's very easy. And the equivalence classes. So if x is an x, then the equivalence class of x is nothing but this thing. Now what is that? This is just a set theoretic notation. This is all those things in the set x such that f of x prime equals f of x. So in general, if y is a point in capital Y, maybe I shouldn't use this color. If y is in capital Y, then f inverse y is defined as those x's such that f of x equals y. Right? It's those points which map to y. This may be empty, so we are not insisting that f is surjective or any such thing. This set may be empty, and this notation is also not meant to indicate that f is invertible or any such thing. It's just a notation for this set. Okay, so these are the equivalence classes, and these are called the fibers of f. Fibers of f. So if this denotes the set of all the equivalence classes, or equivalently the set of all the fibers of f, then we have the following diagram. We have x, we have this map f, and this is y. And this map is pi, which I will define. This is x mod tilde, and that. What is pi? Pi is the map which takes little x to its equivalence class, meaning the set of all the elements which have the same image as x. And what is this arrow that I've drawn here? This I will denote as f bar. And what is its definition? It takes the equivalence class of x and maps it to f of x. Now one should be careful when defining something via representatives, because this equivalence class can have multiple representatives. Basically, equivalence class of x could be equal to equivalence class of x prime. Then we would be obligated to define it also as f of x prime. So it better be the case that whenever equivalence class of x is same as equivalence class of x prime, f of x equals f of x prime. But that is a tautology in this case, because that's how the equivalence classes were defined. So this is a legitimate map, basically. All that is happening here is that the fibers of f, if I may denote it that way, they partition x, and here they just become dots. Since all of these are mapping to the same point here, we may just collapse them to a single dot, and then that dot is mapped to the image of any representative of the fiber. So this is a very, very basic fact. There's nothing very deep going on. It's just a set theoretic fact, and I would like to call it set-theoretic quotienting. We have quotiented out the set X by the fibers of the map F. Okay. So now let us see how we, upgrade that or use that in the setting of our, group theoretic machinery. So let phi be a group homomorphism. The fibers of phi, first of all, we want to show are precisely the left cosets of kernel phi. So first we will identify the fibers of phi, and then we will use the previous thing. The proof is very simple. So let f of g1 equal, this is not f. So phi of g1 equals phi of g2. Basically, we are asking when g1 and g2 are in the same fiber. So of course, g1 and g2 are elements of capital G. Then phi g1, phi g2 inverse equals identity of H, which by properties of group homomorphism is equal to that, which again by the definition that phi is a group homomorphism, we have that, which implies g1, g2 inverse is in the kernel. Maybe, okay, so there's nothing wrong with this, but let me do it in a slightly different way. So then what we will do is that phi g2 inverse phi g1 equals identity of H. It's better this way. What I had written earlier was also correct. So ultimately what we will get is this, which implies phi g2 inverse g1 equals identity of H, which implies this is in the kernel of phi, which implies g1 kernel of phi equals g2 kernel of phi. So what we have shown so far is that if two things are in the same fiber, then they yield the same left coset. In other words, they are in the same left coset. Also, if two things are in the same left coset, then they are in the same fiber. Why? Because if x and y are in the same left coset, then x equals, let's say, gk1 and y equals gk2 for some k1 and k2 in the kernel, implies phi x equals phi g times phi k1 and phi y equals phi g times phi k2. But k1 and k2 are in the kernel, and hence they are identity of H, k1 and k2 are in the kernel, so phi k1 and phi k2 are identity of H, and therefore I can erase this. So if two things are in the same left coset, then they are also in the same fiber because their images are the same. So the first one showed that if two things have the same image, meaning two things are in the same fiber, then they are in the same left coset. And this shows that if two things are in the same left coset, then they are in the same fiber. And therefore the left cosets and the fibers are precisely the same thing. Okay, so this is a simple lemma. And now we move forward. So what we get so far is the diagram. We have the group G, we have this homomorphism H, and for purely set theoretic reasons, we have this diagram, phi bar. Again, G mod curve phi is the set of all the left cosets of kernel of phi. As we just showed, this is the set of all the fibers of phi, and hence, by the set theoretic discussion that we just had, we have this diagram where what is pi? Pi is the map, which takes an element little g to the fiber of phi which contains g, but the fiber of phi which contains g is just the corresponding left coset. So that is the map pi. Now here in this diagram, G and H are groups, and this is a group homomorphism. And the question we are asking is, can we upgrade this diagram to a diagram of groups? Meaning what? Meaning, is there a group structure here on this particular set? This is just a set right now. The set of all the left cosets of phi. The set of all the left cosets of kernel phi. Can we upgrade, or can we endow this with a group structure so that this becomes a group homomorphism and that becomes a group homomorphism? So that this diagram entirely becomes a group theoretic diagram rather than just a set theoretic diagram. Also, we would like to know how many such group structures are there. So the answer to that question is not very complicated. So if at all there is a group structure here such that pi is a group homomorphism, then what we must have is pi g1 g2 equals pi g1 star pi g2, where star is the binary operation on g mod curve phi. So if at all there is a group structure, if at all there is a binary operation such that this becomes a group and this is a group homomorphism, we must have this, which means what? We must have g1 g2 kernel phi, very bad, g1 g2 kernel phi equals g1 kernel phi star g2 kernel phi. So the only candidate for star is this equation. This is how star better be defined, right? It's not clear that such a star even makes sense, because again, these are defined by representatives. G1 could be replaced by any element G1 prime, where such that the corresponding left coset G1 prime kernel phi is equal to that. Similarly for G2, and here we would a priori get possibly a different left coset. However, as we just saw in the beginning of this lecture, that if we define this star as simply this in this fashion, what happened to that? This one, just producting pointwise, then we do have that equation. So this is how we will define star. So define star as, let me write a comma b. So they are left cosets. Going to AB, which we defined earlier, is just a times b, little a in capital A, little b in capital B. Right, so this at least satisfies this equation. It's not clear that this actually makes G mod curve phi into a group, but this equation is satisfied. So now let us just verify that this indeed endows G mod curve phi with a group structure. So that's the final thing. So we claim that this equipped with star is a group. So what do we need to check? First of all, associativity. So G1 kernel phi, G2 kernel phi, and G3 kernel phi. This is what? This is equal to, by definition, G1, G2, not by definition, but by the lemma that we discussed in the opening of this lecture, equal to that, which is equal to G1, G2, G3. So this goes away, kernel phi, which is by associativity of the original group G, equal to that, which is equal to G1 kernel phi. Well, I did not write a star here. I mean, what I should do is write a star here, but I'm suppressing that, as we do. Which is equal to G1 kernel phi, G2 kernel phi, G3 kernel phi. So this shows associativity. The second is identity. Well, this is clear because identity of G times kernel phi, which we just, of course, simply write as kernel phi. So this serves as the identity of this particular binary operation. So I'll leave that for you to convince yourself with. The last is inverse. This is also clear because if you pick an arbitrary element of the G mod kernel phi, the inverse can be easily guessed, which is equal to that. So this is GG inverse kernel phi, which is equal to kernel phi, which is the identity of G mod kernel phi. So this is indeed a group. Okay, to summarize, we had a diagram of sets where this above thing was living in the world of groups. So we wanted to upgrade the structure of this guy to a group. It's a natural thing to ask for. It may be too much to ask for a priori, but turns out that there is a unique candidate for a group structure here such that pi becomes a group homomorphism. That candidate is given by this equation, and we saw that this equation makes sense if we just, there's only one candidate for star basically, and it turns out that it just pointwise, take pointwise product and put everything in a box. So that is the candidate for star, which makes this into a group homomorphism and this into a group. Lastly, we need to check that this also becomes a group homomorphism. So that's the last thing. So claim is that phi bar is a homomorphism. All right. So we have phi bar G1 kernel phi times G2 kernel phi. This is phi bar G1 G2 kernel phi. But what is this equal to? This is the fiber of phi corresponding to G1 G2. So phi bar just maps it to that. That's the definition of phi bar. So I should have said phi bar just maps it to the image of that. That's the definition of phi bar. So this is equal to phi G1, phi G2 by the fact that phi is a group homomorphism. But then again, the first thing is phi bar G1 kernel phi. And the second is phi bar G2 kernel phi. Right? And therefore, phi bar is a group homomorphism. All right. So this thing is called the first isomorphism theorem. Given any group homomorphism, you can factor it out into two parts. So this is called the natural projection map. Natural projection onto G mod kernel phi. Let me write that. So this is the natural projection. So what was I saying? So you have any group homomorphism. You can factor it out via the natural projection to the set of all the left cosets of the kernel and get another group homomorphism. So this is sort of a smaller group, right? If kernel phi is not trivial, it is not the identity map. This is collapsing some elements in G and putting them as a single dot. So you have a kind of a simpler homomorphism phi bar now, which you can use to study the original map phi and so on. So that's what this is. The first isomorphism theorem is just basically this statement, this diagram, where we need to be aware what is the group structure here. Okay, so we will, as we go along, become more and more comfortable with these things because this will be used over and over all the time. All right, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.